avanti. Ok. Buongiorno, questa è la registrazione della prima parte della lezione di 17 novembre. Lo scopo della lezione di oggi di andare avanti con la probabilità certamente io soprattutto vorrei dedicare nostra lezione a cosiddetta probabilità discreta. Significa noi abbiamo un insieme omega, abbiamo detto. Omega ha numero di elementi finito. Per il momento non lavoriamo su un intervallo o qualche, diciamo, probabilità che in generale sarà continua. Discreta significa che il nostro insieme, dove possiamo definire eventi e loro probabilità, è insieme con numero di elementi o, come abbiamo detto, numero di elementi e l'altra volta con questo simbolo usavamo per definire quando il nostro insieme ha numero di elementi finito. Il numero di elementi era, per il numero di elementi abbiamo questo simbolo. Ok? Poi avevamo una specie di algebra di sottoinsiemi. Ricordiamoci, l'algebra significava che noi potevamo prendere intersezione, unione, l'insieme complementare. Per esempio, se il nostro insieme è sottoinsieme di omega e appartiene a questa algebra omega, che cosa sappiamo? Sappiamo per esempio che l'insieme complementare, che è omega meno nostro insieme, che è formato da tutti elementi x che appartengono a omega, ma tali che x non appartiene ad u, l'insieme complementare, anche questo insieme appartiene alla algebra. Ok? Poi se...
Professore?
Prego.
Scusi, potrebbe parlare in inglese?
Of course, of course, of course. Sempre dimentico. Grazie. Ah, ecco, c'era avviso probabilmente in chat. Oh, of course, sorry, Sayed. I am repeating the main part of probability space, the fact that probability space was formed by a set with finite number of elements. Then we have algebra of sets. This is so-called a space of events. So our events, for example, any set belonging to this algebra shall be called even. And then we had function p that associates with at any u belonging to our algebra, associates number probability of u that is belonging to the interval 0, 1. Of course, we can mention properties of this algebra. Let me recall you that algebra means we can take union, intersection, complementary. So say if u and v belongs to our algebra, then we know that u intersect v, union with v belongs to our algebra. And this property is important. In particular, we know that empty set with our algebra This is by definition. And also the whole set omega belongs to our algebra. These are the main properties of our algebra. We can connect it, say, these are the properties of our algebra, while the properties of the probability function P was the fact that if U intersected with V is empty, if they are disjoint, then and belong to our algebra. I shall put only this letter A when omega is clear. I shall not repeat any time A of omega to save space. Then we can say that probability of U union with V is probability of U plus probability of V. Have in mind that there is no formula for the intersection, at least for the moment. We haven't explicit formula. The important property is this additivity property. Then, in particular, this means U. This probability of empty set, because this is element of our algebra, is 0. And if we take the whole set omega, it shall be 1. Essentially, these are the important properties of our probability. So this is additivity, and our examples started with the following simple set. Our typical example was omega was the set 1, 2, and so on, n. So we have n elements, and of course we can say that our algebra of omega is formed by all subsets. And in this sense, we can take as U, for example, if we take U equal 1 only, this is one event, one element of our algebra. We call this U1. If we take all sets with one element, of course, this is element of our algebra, and therefore we can call them event. Let's clean these two lines in order to finish our example. And in this way, we take this U1 is 1. The other set U2 is 2. And so on. We have UN is n. This is set formed by one element, set formed by 1, 2, and this is the set formed by one element n. We can easily see that U1 union U2 union and so on, union of UN is the whole set omega. So if you take each couple U1, U2 or U3, U2, intersection obviously is empty. So we can apply a formula and say probability of omega is probability of U1 plus probability of U2 plus probability of UN. Of course, we know that the whole probability of the whole set is 1, Therefore, here the question is, when we make this model, to say, shall we have the same probability for each of these events? For example, if we extract, we can say some, or if you make some measurement, if is it true that probability for each of this event is equal? Therefore, we can speak about, let me take the precise notion. I think it was one moment. Okay. Equiprobably, therefore, they have the same probability. We have the same probability. P of U1 is equal P of U2 is equal P of UN. So this condition is something that we put as extra condition starting with our model. So if our model is, if we, for example, have to choose from cards, 52 cards, one card, and we are asked if this card is, for example, number 1, blue, or heart, there is this sign, black heart number 1. What is the probability? Of course, to have this card on another card is the same if the cards are, how to say, honest cards. So if they're, when you see from behind, they are the same. And you put some sign on the card, the condition is not satisfied. So depends on the real model, the real situation. And therefore, our idealistic model starts with the case when all probabilities of these events equal, let us say equal to P. And then we can always using additivity property, and from this relation deduce that n times P is equal 1. So from here we can recover this probability and decide that from here we have probability of the event to have 1 is 1 over n. It is clear that in this way we can proceed further, and simply we can take for so-called equiprobability spaces where all probabilities of one event of a set of one element are equal, then we can take any u that is subset of omega of our set, and we know that this is again element. So u has some elements, let's say u has kappa 1, kappa L, where this kappa 1, kappa L are among these numbers, and they're, so we can say that for each of these, for this set can be represented as a union of L subsets of one element. And since for one element we have probability 1 over n, we can say that the probability of this set U shall be L times probability to have event that is formed by set of one element, and therefore we have L over n, and this practically means here we measure the number of elements of U and divide by number of elements omega. This is the classical probability where we assume that we have equiprobability space where probabilities of each of subsets of one element are equal between them, and then the probability for any event, therefore subset, is simply number of elements of U divided by number of elements of all possible events. And our first example that we started last time was connected with the following thing. We have n elements, and we are asking how many orderings of these elements we can do. We said this was kind of a class with 32 students, for example. How many orderings of some exam, for example, can be done? Therefore, we have these 1, 2, let us say 4 elements. And we are asking how many orderings we can make. Ordering, what does it mean? This means we extract. In the first term, we can imagine that an extraction. This is the vote of the written exam of the student. And each of the students have some votes. And according to this vote, we can say, who is the student for this exam is number 3. After this, second result, 2, then 4, then 1. So in this ordering, in this extraction, it is important the order. First is 3, the best result. Second student is second in this list. Fourth student is on 3rd place, and this is the last, the weakest vote in this order. So the question, how many orderings we have, means the following. We have to take this set and make all possible permutations. Permutation means that we have to the same set, the only thing that we change is the ordering. And we are asking how many orderings we have. Last time we had a very simple, result for this. Number of orderings n elements was presented as n factorial. I am not satisfied by the proof I gave, therefore I shall try to explain more clearly. Yes?
I have a question about something before. I get until you said that probability is 1 over n. But then I lost connection and I didn't get the thing about the system, which is U, it's the element K. I lost.
So, as you can see here,
yeah.
U1, U2, UN, these are sets of one element.
Okay, yeah.
But this set does not give us all events. Therefore, we can have other subsets of omega. So our omega is formed by these numbers. And as a first step, we disjoint sets of one element. But we can have one subset that is formed by 2 elements. Therefore, let us suppose that U, here we take U that is formed by L elements. If we say U is of 2 elements, this means U has kappa 1, kappa 2. And as you can see, this set is not like this set where we have only 1 element. So we have 2 elements. If you have 2 elements, how you measure probability? So you represent this set as the set of 1 element union with the set of the other element. So your set of 2 elements is union, disjoint union of 2 sets. So if you want to measure probability, you have to write probability of my kappa 1 plus probability of kappa 2. But this we already know. This is 1 over n. This is 1 over n. Therefore, we shall have 2 times over n. And this means this is 2 is number of elements in U. And here we have number of elements omega. In the previous talk, I took not 2 elements, but I took L elements. And L come Livorno. And in this case, we have to repeat this set, this set. This probability has to be repeated L times. But L is again the number of elements of U. Therefore, for any subset of L elements or number, for any subset, this is the formula that represents the probability. Number of elements in U divided by number of elements of omega. Is it more clear now?
Yes, thank you very much.
Okay. Now we turn to the permutations with example 2 was connected with number of permutations, and we set the following. Example 2 was number of all permutations of n elements. How we measure the number of permutation of elements? We start with, for example, 1, 2, 3, 4. We don't know what is the number of permutation of elements, and I shall denote this number with this symbol, n of n, which means number of permutations of n elements. I am trying to compute n4. For example, what I am doing? If I have 4 elements, I can imagine the permutation as a box. In this box, I have 4 fields where I put my elements. For example, this is the first box, second box, third box, fourth box. So, in the first place, what I can do? So here, how many possibilities I have? Of course, I put here any of these 4 elements because nobody of these elements, no one of these elements is privileged. They are the same. Here, how many possibilities I have? Here I have 4 possibilities. For example, if I take 1 in this place, this is 1 possibility. Second possibility is to put 2. Third possibility is 3. Fourth possibility is 4. So we have 4 possibilities. If already 1 is chosen, how many elements remain? You can count. What is the number of elements that are left? They are one element less because one element is put here. Therefore, if I know that number in which three boxes can be chosen with elements 2, 3, 4, I know this number. This is my number N3. Why? Because I have three boxes and I have to put three elements there. Or these are permutations of three elements. This is when first box is chosen. This is one of the four cases. What is the second possibility? The second possibility is 2, 3, or 4. So in this case, we can say that in order to count all ways to fill my boxes, I have for the first box 4 possibilities, and then I have N3 permutations. So this is N3, number of permutations here. Here I have N3. Here I have N3. Here is N3 permutations of the empty boxes. Empty boxes can be filled with permutations of 3 elements. How many is total number? You have to take this plus this plus this plus this. How many times? 4. So you have this important relation. Of course, the same thing you can do if you have 1, 2, 3 up to n. Therefore, you have n of n shall be n times n minus 1. This means on the first place you have n possibilities because all elements are n. Once you fix this, remaining elements are n minus 1, so you have this number of permutations for n minus 1 elements. And this is your recurrent formula, very simple, that enables you to compute very simply. For example, if you take n of 2, how many possibilities you have? You have 1, 2, and 2, 1. So many? You have 2. This is, of course, 2 factorial, because 2 factorial is 2 by 1. What we can say about N3? According to this relation 1, N3 is 3 times the previous permutation. So we have 3 by N2. And this is 3 by 2 factorial. This is 3 factorial. And 4 is 4 times the previous number, n of 3. And this is 4 by 3 factorial. This gives you 4 factorial. And so on. In general, you get n of n factorial. This is the number of permutations of n elements. And this is important. Combinatorial number n factorial. That means how many reordering we can make from elements, taking into account the ordering. So let me ask if this simple argument is clear, or if you have some question. Probably it's not bad to have the following extension of our problem. Example 3. With the same argument, we are asking a little bit different question. suppose you have n elements. 1, 2, n is your set. And if this is, how to say, the number of students in your class, let us assume that these students, they have to take a bus. But the bus has some places. Unfortunately, number of places of the bus is up to 50% of capacity of the bus. Therefore, we can say that only K students can enter the bus. And the question is, how many orderings of K elements of these students can be found? How many? We can say list of students or ordering or choices of K. How many lists? We can say ordered lists. Ordered. Because we need in our list to have first, second, each student has his own place. If you prefer, these are places in some constant or something like that. But we have ordered lists of K students. Let us make some simulation. Let us suppose to have 4 students totally, and we have to ordered list of two students. In previous example, we have ordered list of n students, so all students we can enter in the list. Now we can put only kappa students, where kappa, of course, is less or equal. Here, easy case is kappa equal n. Therefore, here we shall write smaller than n students. Let us make the example, the simulation. This is combinatorial, small exercises in combinatorics, so they're very pleasant. Some probability theory needs further development, but let us start with these combinatorial questions. So we have 1, 2, 3, 4. Our list now is not by 4 students, only by 2. So we can have a box, but our empty boxes are 2. How many elements we can put in the first place? Can you help me? How many choices we have? Yes?
4.
4 cases. Here we can have 4 possibilities. This can be 1, 2, 3, 4. So once I choose one, for example, here, for this, how many choices I would have? One already is taken. We cannot take the same one. So we have 3. So here we have 3 possibilities. Let us go further. This can be 2. And again, we have 3 possibilities. Here we have 3. Here we have 4. 4 times. So we have the number. Let us say the number. How you choose from 4 elements. List ordered list of 2 elements. This is number of ordered lists of 2 students chosen among 4 students in the class. So, as we said, this is equal. In the first place, we have 4 possibilities. In the second, we have possibility 3. Let us see if we have to choose n, 5, 3. So we have 5 students, and our lists are of 3 boxes. In the first box, we have possibilities. Once we have chosen one of these, remaining for the second box are 5 minus 1, 4. So in the second box, we have 4 possibilities. And once we have chosen the second box, already 2 students are chosen. 5 minus 2 is 3. Remaining possibilities are 3. So this is the number of ordered list to choose 3 students among 5 students. So what is the general requirement? N students, and the list are R. We said kappa. In the first box, we have to start with n. In the second box, already 1 is chosen. We have 1 less, minus 1. In the third box, we have n minus 2. And so on. We have to stop where? How many factors we need here? In totally, we had kappa. Where I have to stop? Can you help me?
n minus k.
Okay, but if I put n minus k, if n is 5, kappa is 3, here I shall have 2. Here I finish with 3. So what is missing? N minus kappa, where I have to finish. Plus 1. This is the correct answer. Because you see, if you count how many boxes you have, in order to have kappa boxes, here you have n. I am writing this as minus kappa minus 1. This is the same. How many factors you have? 1, 2, kappa minus 1, but you have also 0. 0 is one element, n minus 0, n. So totally number of factors here is exactly kappa. If you put here n minus kappa, number of factors shall be kappa plus 1. And this is not correct because you need kappa boxes. Remember that we need here kappa free boxes. Therefore, the correct answer of this example 3 is this. This can be represented very easy. This is equal n factorial divided by kappa factorial. Probably in this way you can remember it more easy. This can be done with the same. If you n minus 1 and so on, the sorry. And this is n minus kappa factorial. Sorry. Simply you put over n minus kappa factorial. So probably this is simpler to be memorized. Only remember that the last term is not n minus kappa, but n minus kappa plus 1. So let us try to see if this argument is clear, if you have something to ask. yes, this is... okay. If this is clear, let us try to do something very simple. Let us try to solve the following problem. We have n students in the class, we have a bus with kappa places, and we have to choose without ordering our students. Any choices we have. How many lists of kappa students without ordering? This means, for example, when you take usual case, we take n equal 4, kappa equal 2. You have at the beginning, 1, 2, 3, 4, and you're choosing 1 and 2. And then you are asking 2 and 1. In previous case, when we have ordered list, these two things are different. But now we say, okay, they are the same. Ordering is not important. It is important to enter in the bus, and then the students are transported from point A to point B. Okay, what we can do now? How we can compute these lists? Again, we can call this n kappa. At the beginning, we said 4 and 2. 4, 2 is number of lists without ordering that are chosen among 4 students. For example, what are the possibilities? Here we can say, okay, first we make ordered lists. This is ordered list. Here we have, for example, E and G. For example, if E is element from here, J is another element, we have ordered list in which you see we have each of these lists in our ordered list, we have repetition because and Ji for us is the same. How many times this is repeated? Remember, here we have 4 times 3. Sorry. In the previous calculation, where at n 4, 2, we had 4 times 3. But in this ordered list, every time where we have chosen E and J, we have also J and T. This is repeated twice. This means if we don't take into account ordered list, we can say that this number of lists is double compared with this number. Therefore, this n2 is 2 times the number that we are looking for. Why 2? Because we have in any ordered, when we make the ordered list, we repeat the choice, EJ, without ordering, is repeated 2 times. Therefore, if we take this choice EJ, counting 2 times, we shall obtain the ordered number. And now you can see this is 4 times 3 divided by 2. So this is the number of disordered lists of CAS students. How we can proceed general? If you have n elements, then you choose E1, E2, E kappa. These are your boxes. But when you when you have ordered this, what you have to do, you can take these elements and you can start to make permutations. Therefore, if this is ordered in this case, then you can take E2, 1, and so on. Here, you can do permutations. And this number shows how many times is repeating your ordered list in a way that you don't distinguish between each two choices. Whenever you make permutation in your ordered list, you get something that is the same for you. Does not you don't care how many permutations you can do, kappa factorial. Therefore, if you take your disordered is n kappa, and when you compare with your ordered permutations n kappa, here we have to put the number of permutations that gives practically the relation between ordered and disordered. Disordered permutations are a much smaller number, and they are proportional with this factor, that is the number of permutation of your elements. Therefore, from here, we can find this number, m, n kappa, that is, we said, this guy, that was n, n minus 1, and so on. What was the last term? N minus kappa, but don't forget plus 1. So we have kappa factors, and this shall be divided by kappa factorial. This number is the number of lists, disordered lists of kappa students chosen among big n students. Here, remember that always kappa is even n, bigger or equal than 0. I should put for the moment 1 here, because I didn't say what is the meaning of when kappa is 0. When you have kappa students, list of at least one student, and here you have evidence. This is the formula. Actually, here in this formula, we can take what will happen when we have kappa equal n. How many lists, disordered lists of n students you can have? Of course, you have only one. You put all students and forget about it. Let us check that when kappa is n, is really we have 1. Let us compute m, n kappa. This is when we take n, I have to start n, n minus 1, and so on. When I put kappa equal n, what is this factor? N minus n plus 1 is 1, divided by n factorial. Now we are sure that in numerator we have n factorial, denominator n factorial, and therefore this is completely compatible with our intuition that we have only one list. Let me ask you if this part of disordered list, choice ordered list, is clear to you, or if you have some problems to clarify or questions. We can see also in our next appointments, if you have some doubts, we can clarify. These coefficients are very important. They are called binomial coefficients. And they have this variable structure. Typically, they appear in this. Let's take another example.
Excuse me.
Yes.
Could you repeat, please? Why did you put n and then after m in the last formula?
After n?
Not there.
Where?
There, where you? Yes.
Here.
No.
These are ordered lists, and these disordered lists.
And the follow formula?
Sorry?
The follow one. When you...
This one?
Yes.
Ah, I use this formula. I substitute kappa with n. So the way is the following. From this, press m, because we know from previous example this guy. So from this relation, I get this one. I get this one. I put kappa equal n in this formula. And when you put kappa equal n, you get n minus 1, n minus n plus 1, that is 1. And below, n factorial. I cannot understand your question. You're asking from where is this relation?
Yes, but now I get it.
This is from here. From here. When kappa is equal n. Sorry, the place for the whiteboard is not big enough, and probably it is better with arrows to clarify the reasoning. Okay, now it's okay?
Yeah, yes, thank you.
Okay, some other questions, please to ask. Don't worry, these points are very important, and we have to clarify them. As you can see here, we have the next example, example 4. That is the following. You have 1 plus x to the power n. And you're asking the following. How you expect this? For example, when you have 3, this is 1 plus one coefficient x plus another coefficient x squared plus, and here is clear, x to the power 3. This is. So how you compute these coefficients? It is clear that you have 1 plus x, 1 plus x, 1 plus x. So as you can see here, you have x to the power 1. But you can interpret this x as students. So you have 3 students, and in order to have x, you have to make a list of 1 student. So here you have m 3 1, because you don't care the ordering. If you take this by 1, you have x, but if you take this by 1, this x by this one, again x. Therefore, you don't care the ordering of your lists. And the coefficient in front of x is this one. If you want x squared, you have students and you have to make lists of 2 students. So you put here M3, 2. Of course, this is M3, 3, but we know that M3, 3 is 1. That's why it is not mistake that I have put this question. After the break, we shall see that this can be expanded for any n, and when you take x to the power kappa, this number is exactly m n kappa. So-called binomial coefficient is coming from this expansion of the binomial. Let us make now a small break, and after the break we shall continue eventually if you have some questions, but we shall this problem. Let me stop the presentation. The registration, yes.